So the scientific way to acquire knowledge is empirical. That means it's based on observation and experiment, as opposed to philosophy, which is thinking about stuff. So the scientific method is a process for understanding nature by observing it and conducting experiments. And the key characteristics of that include observation, formulation of hypotheses, experimentation, and formulation of laws and theories.
I've been getting paid $1,000 a month, if
Oh,
not
we're so
more,
happy for you.
just from this
So
company.
happy for you. It's not even a lot of money.
No, it isn't. It's a little loud. So this is just a little animation about the scientific method. So here's this guy reading a book, listening to a record, very old school. He's got these plants, right? And he observes that the one plant is really tall and the other plant is really short. Right? So there's the observation, right?
The fact that I remember this.
So he's going to measure it, quantify things. Well, how tall are they? And then the question here is, why? Why is one taller than the other? So you come up with a hypothesis. This is what you think might be the answer. And then you have to test the hypotheses. So he's got a couple different ideas. One is he was reading. Maybe that has an effect. Music might have an effect, or sunlight. So he's going to do an experiment, or experiments, to test these things. Okay, so here you measure the plant, and then we're going to read to the plant. And do this every day, and go on and on and on, and see how the plant grows when it's being read to. So we got the one that's being read to and the one that isn't being read to. You have to have a control group. So here, playing music for one of the plants, measuring how it grows, versus the one that doesn't get any music. Again, repeating this every day. These are the sorts of things you might do for like an elementary school science fair. Right? Third test, sunlight. So this plant is next to an open, uncovered window, getting sunshine. This plant, the window is shuttered, so it's not getting much light. Measure the height over the course of time. So this is the experiment. And then looking at the results. No effect from the reading, no effect from the music, big effect from the sunshine. So here is probably bigger over on the left because it was getting more light. So that may seem a little simplistic, but it's simplistic on purpose. You can actually apply this scientific method to lots of things in your life. I find myself doing that. The car starts making a weird noise, right? So what do? I start observing it. Not formally, but kind of informally. It's like, well, does it happen when I'm at a standstill, when the car's cold, when the car's warmed up, when I'm going fast? You know, you look at what affects it. Those are observations. And that allows you to come up with a hypothesis of what might be causing it. So here, in looking at the plants, you know, one is bigger, the other is smaller. Now, I think most of us could have guessed that it's because the one wasn't getting as much light, right? But the hypothesis then, well, this one's not getting as much light. How do you test it? You have to test it. You have to do an experiment to see if that's actually the case. Right? Well, what if your hypothesis is wrong? Your test says it's wrong. Well, sometimes you have to throw out the hypothesis. Other times you just need to change it a little bit. So observations are also known as data. We typically associate that with numerical data, quantitative data, but it can also be qualitative data. Descriptions of characteristics of behavior. So the example in the book is Antoine Lavoisier. He was fascinated, as many chemists are, with things burning. Chemists like to burn things. And so he was looking at the mass of an object before it was burned and after it was burned. But what he was doing is he was burning them inside of a closed container. And what he noticed was that if you look at the total mass of the container before it burns and after it burns, it didn't change. Now we know that you put a log in a fireplace and you burn it in the open, and what's left afterwards weighs a lot less. So this was like different. He's like, huh. So that's the observation. That leads to a hypothesis. A hypothesis, a tentative interpretation or a tentative explanation of the observations. I think this might be why it's doing that. And so he explained his observations of combustion by hypothesizing that when a substance burns, it combines with a component of the air. They didn't know what oxygen was back then. An important thing about a good hypothesis is it needs to be falsifiable. You have to be able to test it and prove it wrong. So if your hypothesis involved undetectable aliens coming down and doing something to the thing that you burned, there's no way you can test that, right? Undetectable aliens, right? You can't detect them. How can you test that? That's not a useful hypothesis. So the hypothesis has to be testable. We should be able to prove it wrong. So we test things by using experiments. And experiments need to be controlled. So when he was looking at the plants, he had this plant that he read to and this plant that he did not read to, and he's measuring both of them at the same time and doing it over the course of days so that he can measure the effect. It has to be controlled. And then the results can either support your hypothesis or prove it wrong. You can't prove a hypothesis to be correct. It's kind of disturbing to think about. You can't prove anything to be correct. So the things that we hold as true are things that no one has been able to disprove yet. So if it's wrong, you either modify your hypothesis or you throw it out entirely. So hypothesis and testing goes on and on and on. And if you look at a summary of past observations that can also predict future events, that can be summarized in a scientific law. So probably the most famous, looking for something I can drop for. Probably one of the most famous scientific laws is the law of gravity, right? So here's a roll of tape. I'm holding it out. What's going to happen to it if I drop it? It's going to fall to the floor. Yep,
Well, now you get a big.
every single time, right? Does it say why? No. The law just says what happens. In Lavoisier's case, what he came up with is the law of conservation of mass. So that in a chemical reaction, matter is neither created nor destroyed. So inside that closed container, he's burning something that's a chemical reaction, but matter is not being created or destroyed because when you weigh the thing, it weighs the same before and after. So we can also test scientific laws, and occasionally, we've got some new insights that allow us to test a law in a different way, and we find out that maybe that law is wrong or a bit misunderstood. The thing about scientific laws is you can't choose whether you're going to obey them or not. Law of gravity, everybody has to obey the law of gravity. You can't decide, I am not going to obey the law of gravity anymore. I'm going to walk off the top of the parking structure. No, you're going to fall. Not a good idea, right? Scientific laws tell us how things behave. They tell us what happens. If we have a hypothesis, or maybe several hypotheses, and they have been rigorously tested, nobody can disprove them, that might form the basis for a scientific theory. So a theory is an attempt to explain why nature is doing what it's doing, right? Not just what it does. So after Lavoisier, John Dalton came up with the atomic theory after a lot of experimentation and hypothesizing. The atomic theory explains the law of conservation of mass by proposing that matter is composed of small indestructible particles called atoms. In a chemical reaction, you're just rearranging the atoms. None of them disappear, no new ones come, so of course the amount of mass is staying the same. So the theory explains the law. Theories are also validated by experiments. You can't conclusively prove a theory to be correct because new discoveries sometimes come along and realize that, oh, well, that was good as far as it went, but we know this other stuff now, so we need to modify that theory. In everyday life, when we say, oh, well, I have a theory, it's like, well, I have an idea, and it's not that significant, right? It's not very meaningful. But in science, when we say this is a theory, that's a big deal. That is something that's been tested by lots of different people. And, scientists tend to be a little skeptical, and somebody, comes out with this new experiment and says, this does this. And then there's a whole bunch of people like, I don't know, I want to see it for myself, right? And that's why we publish papers describing what we did and the results we got, and then other people go, just out of sheer curiosity, and try to replicate the experiment. And hopefully they'll get the same or very similar results that will support your hypothesis, but occasionally there's somebody who's engaging in fraudulent behavior, right? They want this to be true, and so they kind of tweak things along, but when other people go to repeat it, they can't repeat it because it wasn't true to start with.
Yeah, I remember the 116, it takes it up.
Mm.
That guy falsified that he found element 116.
Yeah, there's lots of examples. So the scientific method is not a set of steps. Do this, do this, do this, do this. It's just an approach, right? So this is kind of how it might work. So you've got an observation, you come up with a hypothesis. So then we need to test the hypothesis. The test may confirm the hypothesis, or the test may disprove the hypothesis. So if it doesn't prove it correct, then we have to revise it or toss it out and start over again. A bunch of observations can also lead to a law, which also can be tested with being confirmed or revised. And hypotheses can lead to theories, which are also tested and confirmed or revised. And so the process of science, a lot of it is going around in this loop right here. Revising the hypothesis, testing it again. Revising the hypothesis, testing it again. And one of the interesting things about science, is really you spend most of your career trying to prove yourself wrong. You can't prove yourself right. So you go around trying to prove things wrong. And that's why I think scientists are generally comfortable with failing, right? And that was really made aware to me in the that difference in thought during the pandemic. And you hear, politicians, and they come out, and nobody knew what COVID was or where it was going to go or anything. Nobody knew anything, right? So the scientists, put out this hypothesis. We think this is how it's working, and this is what we should do. And then they come out the next month and they say, no, we're not going to do that. We need to do this other thing. And that's how science works. When you get new information, you change your ideas. But most people looking at that, they're used to looking at politicians who, they come out and say something and they're going to stick to it, darn it, because if you change your mind, the public thinks you're wishy-washy. Well, it turns out that changing your mind based on new information is very smart. Just holding to your original idea, despite new information that disproves it, that's just really, really stupid. And so, one of the things I would love is this, if everyone just got a better idea of what the process of science is, because I think it's often very misunderstood. Scientists are investigating things that we don't know. That's why we're investigating them. And it's not like doing a problem on mastering chemistry where it says, yes, you're right, or no, you're wrong. Nobody knows what the right answer is. We're trying to figure that out. So it's actually kind of messy. Does anybody have any questions? Okay, so this will help us see if we understood some of that. So which of these statements best explains the difference between a law and a theory? So A, a law is truth, a theory is mere speculation. B, a law summarizes a series of related observations, a theory gives the underlying reasons for them. Or C, a theory describes what nature does, a law describes why nature does it. Anybody want to take a chance? C. Okay, so C is very tempting because of how it is worded, and they did it on purpose. It's worded very similarly to the definitions that we were given previously, but it's exactly backwards. So the theory describes why, the law describes what. So what's a better choice? B. Okay. So B is the actual answer.
Technically, a law is the potential of what?
The potential of what?
Yeah, because if nothing can be proved right, the law would be potentially what is right.
Well, a law is just saying what happens. So, the law of gravity predicts what's going to happen if I drop the roll of tape, right? It falls to the ground. But the theory explains why that happens. And the interesting thing about gravity is they're still arguing about what gravity is exactly. Still haven't quite figured that one out. Any questions? I appreciate you guys being willing to answer things, because it's good to be, it's absolutely fine to be wrong sometimes. What am I doing?